The inverse of function f is denoted f to the negative first power is what it looks like here, guys. But that's just our notation. So that's what it's going to look like there to show the inverse. The notation f of x tells us the relation is a function, but its inverse may or may not be a function. So we're going to consider the function here f of x equals the square root of x minus 2. We want to know our domain and our range of f. So our domain deals with our x's, our range deals with our y's. When we look here, our domain always starts off, and same with our range, as all real numbers. And then we exclude anything we can't have. Here we have a square root, and we know that square roots cannot equal, we can't take the square root of a negative number. So here I take whatever's inside my square root, and it has to be greater than or equal to 0. Again, we can't take the square root of a negative number. I add 2. So my domain is either x is greater than or equal to 2, or we can do all real numbers greater than or equal to 2. For my range, that's all the outputs that I'll get. Okay, we know that our range here, because we have the positive square root, that means we can get 0, like if I plug in 2, 2 minus 2 is 0, square root of 0 is 0, or anything positive. We can't get anything negative. So here, all real numbers greater than or equal to 0, or y greater than or equal to 0. And again, that's because we have the positive square root here. So everything that we get is going to be 0 or positive. Domain, range. Now, it wants us to find our inverse. F of x, guys, is just like a y. It's just written in function notation to let us know it's a function. So what I have right now is y equals the square root of x minus 2. Again, to find the inverse, we are going to swap our x and our y and keep the rest of our equation exactly as it's written. Now, we need to solve for y again. So to get rid of a square root, we're going to square both sides. And to get rid of subtraction, we add 2. So I have y equals x squared plus 2. Or I can do my inverse equals x squared plus 2. And again, this is just a notation just like f of x. We want to know what are the domain and range of our inverse. So because we're only dealing with the positive root here, guys, we need to be careful. Our domain and range of our inverse are going to be from the domain and range of our initial function. So here, my range goes to my domain, and my domain goes to my range. We swap our x's and our y's. So if we look at our inverse function, it looks like we can have anything there because we can plug in any number to be squared and then add 2. But since we're only dealing with the positive square root, our domain and range are still going to come from that original function, and we're going to have restricted domain and restricted domain. So my domain is now going to be all real numbers greater than or equal to 0, or x greater than or equal to 0, again, from the range of my original function. And the range of my inverse is going to be y greater than or equal to 2, or all real numbers greater than or equal to 2. And again, that comes from the domain of my original function. And we want to know, is the inverse a function? Here it would pass the vertical line test if we were to graph it. We would just have the one branch of our parabola. So it would be something kind of like this. and that's fine. Pass our vertical line test. There's no plus or minus square roots in there. There's no absolute value that we have to kind of worry about. There's no division. There's nothing to tell us that it wouldn't be a function. So, yes. Now, based off G here, go ahead and pause and give this a try if you'd like. We want to know the range and domain of G. Remember, domain deals with x's, range deals with y's. Here, there's nothing that we can't plug in. Okay, I can plug in any numbers I want to in for x. There's no square roots, no absolute value, no division by 0, nothing to indicate that we can't just plug in any number we want to. So my domain here is all real numbers. My range is also going to be all real numbers. Okay, there's no number that we wouldn't get. Okay, this is linear because we have just x to the first power. It's linear, it's a line. We draw our arrows in both directions, and we could get any number potentially. The inverse here, again, g of x is just like y. So we have y equals 6 minus 4x. We're going to swap our variables. So instead of writing y, I write an x. Instead of writing x, I write a y. And the rest of my equation stays as it is. Now, we solve for y again. Subtract 6. Don't forget to bring that sign down with your number. Then we divide by -4. And when we do that, we do it to every piece. So I have -1/4 x plus 3/2 equals y. And again, we can change that to equals our inverse notation there if we want it as well. The domain and range of our inverse, sorry, this is G, not F. The domain comes from the range of our original function, which we said was all real numbers. And the range comes from the domain of our original function, which we said was all real numbers as well. So our domain and range of this function are still all real numbers. And we want to know, is it a function? There's no reason that it wouldn't be. It is still just a line. So yes, we have nothing to indicate that it's not a function. No plus or minuses, no weird stuff happening in there. It's still just a line. Functions that model real-world behaviors have meaningful variables. When this happens, it's better to leave the variables in place and solve for the other variables, as shown on the bottom of page 407. So when we're talking about specific things like distance and time, it's easier to solve for the variable than it is to swap them around. It helps us make sure that we're talking about the right things still. So we're plugging the right variables into the right places. We're still talking about time or distance or whatever it happens to be. The function d equals 4.9 t squared represents the distance d in meters that an object falls in t seconds due to Earth's gravity. Find the inverse of this function. Okay, so that's the first thing we're going to do is find the inverse. I have d equals 4.9 t squared. So we are just going to solve for t here. First thing I'm going to do is divide to get t squared by itself. And then to get rid of my square root, or my square, I'm going to take the square root. So I get the square root of d over 4.9 equals t. Usually here we do plus or minus, but t is time in seconds. I can't have negative time, so it's just the positive square root here. Now, we want to know how long in seconds does it take for the cliff diver shown on page 408 to reach the water below. It tells us on page 408 that the distance is 24, so we're going to plug that in here. and calculate it to get about 2.2 seconds. Feel free to pause here and give this a try if you'd like. Now, the function d equals v squared over 19.6 relates the distance d in meters that an object has fallen to its velocity v in meters per second. Find the inverse of this function. What is the velocity of the cliff diver in meters per second as he enters the water? So again, my inverse, I'm going to solve for my opposite variable. First step is to multiply to get rid of my division. And to get rid of my square, I'm going to take the square root. And again, when we take the square root, we usually do plus or minus, but we're not going to have a negative velocity here. So that is my inverse. Now, this diver is the same diver from problem 5, so we have a distance of 24 meters. I'm going to substitute that in for d. Here I get the square root when I multiply of 470.4. And when I take the square root there, I get about 21.7 meters per second. And that is the velocity of the cliff diver as he enters the water. I'm going to stop here and continue our last example in a new video.